Today's lecture is going to be about closure properties of regular languages. We have talked about this. In previous lectures, we showed that regular languages are closed under union, concatenation, and star. And these are the regular operations. These are the operations that we call regular operations. Now, regular languages are closed under other operations, including intersection. So regular languages are closed. Well, first, before intersection, they are closed under complementation. Complementation, the complement. So, meaning if L is regular, then the complement of L is regular. How did we prove this? That if L is regular, then the complement of L is regular. So we showed how to construct an NFA or a DFA for the complement. DFA, yeah. So if you have a DFA for a language, you can construct a DFA for the complement by swapping accept and non-accept states. So regular languages are closed under complementation. Now, regular languages are closed under intersection. Now, we didn't show this in great details, but I mentioned the idea in a previous lecture. How, given DFAs for two languages, DFA for L1 and a DFA for L2, and this DFA has, states P0 or let's call them Q0, Q1, Q2 through Qn, and this has R0, R1, R2 through Rm. So the number of states can be different. How would you construct a DFA for the intersection? Systematically, how can you construct a DFA for the intersection? So you would construct a DFA that has the cross product of these states. So you have a DFA that has Q0, R0, Q0, R1 through Q0, Rn, M, and then you have Q1, R0, Qn, R0, and this is going to be Qn, Rm. So you have the cross product of the states, and basically you track the two states simultaneously. Whenever a transition happens, you track both states, and each state in this intersection DFA, or a DFA that represents the intersection, each state in there tracks two states in, the state in L1 and the state, or the state in DFA1 and the state in DFA2. So this description is not detailed, but it just gives you the idea how you can construct a DFA for the intersection. But we can, in a previous lecture, we said that we can prove mathematically that regular languages are closed under intersection. Without showing how to construct a DFA for the intersection, if L1 is regular and L2 is regular, then L1 intersection L2 is regular. By the way, this is important because then, after we're done with the regular languages, we will look into another family of languages, which is context-free languages, and those will not be closed under intersection. So it's not all families of languages are closed under intersection. So it's like, don't assume that any family of languages is closed under intersection, and we'll show that when we get there. Okay. So, how do we prove this mathematically? Using what we have proven. Union, concatenation, star, complementation. How do we prove the intersection? Well, in set relations, or set operations, what's the relation between the intersection and the union? What law defines the relation between intersection and union in set theory? So there is a law. What's the name of the law that defines the relation between intersection and? So that's De Morgan's law. So De Morgan's law is, so if you have L1 intersection, the complement of L1 intersection L2 is what? The complement of L1 union complement of L2. Well, if you take the complement of both sides, so if you say the complement of L1 intersection L2 is the complement of this. So this defines, so the complement of L1 intersection L2 is L1 intersection L2. So this is, L1 intersection L2 equals the complement of L1 intersection L2, and it's the complement of this. Now this gives you the intersection relation in terms of the union relation and the complement relation. And we have shown that regular languages are closed under union and complementation. Therefore, they are closed under intersection. Okay. So this, De Morgan's law tells us that, since we can define intersection in terms of union and complementation, then regular languages are closed under intersection. Now, what about subtraction? L1 is regular and L2 is regular. Is L1 minus L2 regular? Again, using set relations, set operations or properties, or the relations between the different set operations. What's the relation between subtraction and other operations that we have talked about? Can you express L1 minus L2 using another set or other set operations? What's the subtraction? When you subtract,
It's different.
subtraction can be expressed in terms of, so this is L1 and this is L2. So subtracting L2 from L1, so this is L1. So this is L1 minus L2. right? So this is in blue is L1 minus L2. Can you express this using? It's the intersection between. It's not the intersection between L1 and L2. It's the intersection between L1 and the complement of L2. So this is the big set, which is in our case sigma star. So this is in our case the set that contains both sets, which is sigma star. So this is the intersection between L1 and the complement of L2. So this is L1 intersection complement of L2. And since we have proven that regular languages are closed under intersection and complementation, then regular languages are closed under subtraction. Because we have managed to express subtraction in terms of intersection and complementation. Okay, so let's see what other interesting interesting operations we have. So there is the reversal. Let's talk about the reversal operation. Reversal. Now if you have string S, which is equal to A1, A2, A3 through AN, the reverse string S R is AN minus 1, A2, A1. Or just do this. Very, very straightforward definition. So if you have, 1, 0, 1, 1, the reverse string of this is 1, 1, 0, 1. Very intuitive. Now what's the reverse of a language? The reverse language of a language, or of a formal language, is the language that consists of the reverse strings of the strings in L. So LR equals WR such that W belongs to L. So an example, is, if you have L equals 0, 1, 1, 1, 0, 0, 1, 1, then the reverse language of this is 1, 1, 0, the reverse of this, and 1, 1, 0, 0, 1. So we just reverse the strings. Right? Can the reverse language be equal to the original language? Yes, it can. Under what condition? Well, more general. Yeah, if all the strings, that's one case. Yeah, if all the strings consist of one symbol, so if you reverse them, they will stay the same. Now, what do we call a string that if reversed stays the same? Have you heard of palindrome? Yeah, palindrome is a string, if reversed, stays the same. So like, if L consists of palindromes, like 101 and 11011, So the strings in this language are palindromes, so the reverse language is the same language. So this is, do all the strings have to be palindromes in order for the reverse to be equal to the language? No, not necessarily. Give me a language in which the strings are not palindromes. Well, yeah, so you can, for example, say 110 and 011. So these are not palindromes, but when you reverse it, LR is going to be 011 and 110. So if the strings are the reverse of each other, the strings in the language are the reverse of each other, then the reverse language is going to be equal to the original language. Now, what we are interested in here is the regularity of reverse languages. If the language is regular, is its reverse regular? And this is something that we can show easily, this time by showing how to construct an NFA for the reverse language. So consider L W such that W starts with 1 or ends with 0. So how do we construct an NFA for this in a straightforward manner? So we have, this is the union of two languages. Starts with 1. Starts with 1, which is 1. Then you can have anything. Or ends with 0, so you can have anything. And end with 0. Right? So this is start with 1, this is end with 0. Now, in order to construct an NFA for the reverse language, how do you think we can construct an NFA for the reverse language? We have an NFA for this language. How do you think we can construct? It's very intuitive. How can you construct an NFA for the reverse language?
Either 0 or end with 1.
In general, yeah. Generally speaking, you have an NFA for a language. What's the logical and intuitive way of constructing an NFA for the reverse language? So what should you do with the transitions? Reverse, yeah, you should reverse every transition, and you should swap start states with accept states. But how can you do that if you have one start state, but you can potentially have or possibly have multiple accept states? So how can you do the swapping if you have a single start state and multiple accept states? In fact, it's always possible in an NFA, it's always possible to convert it into an NFA with a single accept state. How? How can I convert this NFA into an NFA with a single accept state?
Just make an epsilon transition.
Yeah, exactly. So this is the flexibility of the NFA. Epsilon, epsilon, and then this is my master accept state, and these are no longer accept states. So just make all accept states point or go into one master accept state via epsilon transitions. Then I have unified the accept states. Now reversing the NFA will be straightforward. Right? So this is NFA for L. And NFA for LR is going to can be constructed in a straightforward manner. NFA for LR, so this becomes your becomes your start state, and then you have these epsilons, and then you have 0, 1, and then it goes to this and then epsilon, and this becomes your accept state, 0, 1, and this is a 1. So I'm reversing this, then I reverse this, so this is 0, and so it becomes ends with 1 or starts with 0, which is the reverse. Right, and this is an epsilon transition. What else is missing? Does it look like an NFA for the reverse language? Yes, in fact, it's it's quite intuitive that if a language is regular, its reverse language is regular, because it's just basically you're looking at the strings in the other direction. So it's clearly the same thing, but it's in reverse order. So it's quite intuitive. Okay, so now how many operations have we proven closure under for regular languages? So we have proven closure under union, concatenation, star, intersection, complementation, and reversal, and subtraction. Okay. All right. So one more thing. Well, let's do now some prove and disprove questions on these concepts, the concepts of closure properties of regular languages. So let's do some prove and disprove. If L consists of a finite number of strings, then L is necessarily regular. If L consists of a finite number of strings, then L is necessarily regular. Is this true or false? If it's true, how would we prove it? If it's false, you just need a counterexample. So for false, you need only one counterexample. For true, you need to prove it. So is this true or false? What do you think?
True.
Why true? How would you prove it?
Construct the strings.
Do what?
You can construct each string and a set of just the string. That language should be regular. And then you can union all of that. And it's regular because of the it's closed under concatenation, but it's closed under union, and so you can construct it from there.
Yeah, exactly. It follows immediately from closure under union. So if you have L that consists of S1, S2, S3 through Sn, now there is a finite number of strings in it. So you can show this using an NFA. In fact, you can easily construct a regular expression. So in order to show that a language is regular, you can give either a DFA or an NFA or a regular expression. You have three options. And here, in fact, the easiest option is the regular expression. Do you know what the regular expression for this is going to look like? Yeah, it's just going to be S1, union S2, union S3, union Sn. This is a valid regular expression. Why? Because what can we use in regular expressions? We can use union, concatenation or star, and we can use the symbols of the alphabet. What have we used here? We have used the symbols of the alphabet, right? And the union. So this is a valid regular expression for any language that has a finite number of strings. Now, why can't we do this for a language that has an infinite number of strings? Because a regular expression cannot have an infinite number of symbols in it. So a regular expression must be finite. You cannot have an infinite regular expression. You cannot say, you cannot say this in regular expressions. A regular expression must have a finite number of symbols in it. And of course, if you want to do an NFA, then you can easily do an NFA. So this is, then you have an NFA for S1, just an NFA that accepts a single string, trivial. Then NFA for S2, then NFA for S sub n. If you want to do it with NFAs. Yes?
Wouldn't that one, that it starts with the 1 and ends with the 0, wouldn't that be an infinite amount of strings?
Yeah, this has an infinite number of strings, yeah. So we never said that this has a finite number of strings.
Didn't you say in order to be a regular expression it needed to be finite?
No, I said the other way around. There's a huge difference between saying that a language that consists of a finite number of strings is regular and saying that every regular language must consist of a finite number of strings. I mean, if we say that a regular language must consist of a finite number of strings, then regular languages would be trivial and would be very limited and won't be as interesting. No, there are regular languages that have an infinite number of strings. We just said that every language that consists of a finite number of strings is necessarily regular. Okay. And in fact, we can add that all the interesting regular languages consist of an infinite number of strings. So the notion of interesting is that's hard to define, or can't be defined. So let's take another example. Okay, if L1 and L2 are regular, and L1 is a subset of L3 and L3 is a subset of L2, then L3 is regular. Is this true or false? So, of course, this is true. Is this true or false? If L1 and L2 are regular and L1 is a subset of L1 is a subset of L3 and L3 is a subset of L2, then L3 is regular. Well, I think it will always be easier to try to think that or assume that it's false and try to come up with a counter example. If you come up with a counter example, you disprove it. If you can't come up with a counter example, then you try to prove it. Yes?
It's false because L1 and L2, oh wait, no, if L3
Yes,
is
it's false.
inside L2.
It's false. Yeah, but why? So give me a counter example.
Well, I mean, I misread it and I thought L1 was a subset of L2 and L2 was a subset of L3, so now I don't know how to prove it.
Okay, no, the L3 is like L3 is the one in between. So it's, this is regular and this is regular. Is the language that is a subset of the big one and a superset of the small one,
Well,
is it necessarily regular?
okay, to be regular, it needs to have a set of strings and...
It's okay, so the answer is much easier. Think in a counter example and always use trivial languages to give you easy examples. Yes?
So you can let L2 be sigma star, which
Yeah.
is regular because that's a regular expression. And you can let L1 be the empty language.
Yeah.
And then choose any non-regular language.
Then all languages satisfy this. Yeah. So it's basically this is obviously wrong. If L2 is sigma star, which has all the strings, and phi, which has no strings, so this is valid for any language. So this would imply that any language is regular, but it's not, you can just come up with any language that is not regular. So let L1 equals phi, L2 equals sigma star, L3 equals the language, one of the languages that we know are non-regular, which is AN, BN, our famous non-regular language that we proved last time to be non-regular, and greater than or equal to 0. So in this case, you need to explain this, L1, L3, L2, but L1 and L2 are regular. Why? Because they are regular expressions. They are already regular expressions, are regular, but L3 is not. Okay. So another one. If L1 is regular, then the language L2 that consists of all the strings in L1 that start with 100 and do not end with 010 is regular. Is this true or false, and how would you prove it or disprove it? So we're saying L1 is a regular language and L2 is related to L1. It's L1, but it has only the strings that start with 100 and do not end with 010. So think of this in terms of set relations, right? What's the so let L3 be, sigma, the language, the strings that start with 100 be generated by 100 sigma star. So this is the language where the strings start with 100, and L4 be generated by what?
Sigma star.
Sigma star
010.
010. Now what's the relation between now L2 equals? What's the relation between L2 now? How can you express L2 in terms of L1, L3, and L4? It's straightforward, right? So L2 equals L1 intersected with
The union of
intersected with L3 intersected with the complement of L4. Right? So L1 intersected with L3 intersected with the complement of L4. Now, okay, so what can you say about L3 and L4? They're clearly regular because there is a regular expression. So this is regular and this is regular. So all of them are regular, and these are operations that we proved to be, that we proved our regular languages are closed under. So since L1, L3, and L4 are regular, and we have shown that regular languages are closed under intersection and complementation. L2 must be what?
Regular.
Regular. Okay, let me give one more example. Any questions on this example? Okay. If L1 is regular and L1 intersection L2 is regular, then L2 is regular. If L1 is regular and L1 intersection L2 is regular, then L2 is regular. False, yes, it's false. What's the counter example?
L1 equals AB, and then
L1 equals,
AB, and then, or
what do you mean AB?
like just the single string AB, and then L2 could be A to the N, B to the N.
Okay, AB, and L2 is AN, BN, N greater than or equal to 0. So this is clearly regular. And this is just one string, sorry. This is string AB. And this is non-regular. So the intersection, L1 intersection L2 equals what? Equals L1, which is AB, which is regular. But L2 is not regular. So the intersection is regular, but L2 is not regular. Okay, so let me give the last example. Okay, if L1 and L2 are regular, then L, which is equal to W, such that W belongs to L1 and W reverse belongs to L2 is regular. Okay. Okay, so is this true or false? and y. Okay, so it looks like L can be expressed using L1 and L2 and some set relations. So we have the reversal relation, which is, we have shown that regular languages are closed under. So this definition has like, the and is what? No, the and is intersection. The and is intersection, and this is reversal. So in fact, when you say WR belongs to L2, it's equivalent to saying that W belongs to
Reverse of L2?
yeah, the reverse of L2. If WR belongs to L2, then W itself belongs to the reverse of L2. Right? If a string belongs to L2, then its reverse belongs to the reverse language. Because by definition, the reverse language is the language that has the reverse strings. So, you know, this is L, 10, 11, 11, 10. LR is what? 1101, 0111. So if WR, so if this is, these are the W's. So if WR belongs to L2, then W belongs to L reverse, or in fact the other way around. It's, if this is W that belongs to L reverse, then WR if WR belongs to a certain language, then W belongs to the reverse of that language. So here WR belongs to this language. Let's say this is L2. WR belongs to L2, then W belongs to L2 reverse. So this means that L equals L1, what intersected with L2 reverse. L1 is L is L1 intersected with L2 reverse, and we have proven that, I'm not going to write it, we have proven that regular languages are closed under intersection and are closed under reversal, so this language will be regular. Okay, you can write it down. I'm not going to write it because I'm going to end the lecture now and talk about the quiz.